Hello, welcome back to Mr. Newton's chemistry series for AP Chem. We're looking at acid-base equilibria here. This is part one. This is kind of more or less an introduction to acid-base equilibria, but important to note that of all the concepts that show up on the test, this one does end up coming up the most, and guaranteed you'll see a free response question dealing with this. So we want to cover this in detail and do as much practice and learning as possible. So we're really good and really proficient at acid-base equilibria. So part one here, we're going to talk about the Arrhenius concept, which is kind of the idea that you probably already know from general chem, and strong bases and acids, something that you're probably already familiar with, and just sort of go over how does that fit into acid-base equilibria and what do you need to know from that. And this is sort of previous learning in some senses, but the very important base. So we could actually call this the intro. So let's call this intro here. I'm going to use a different color just for fun. All right, so if I said that I had HCl, this would probably be a gas. So if I had HCl, then if I did dissolve that into solution, that would become hydrogen ions in there and chlorine ions in there. And so according to Arrhenius, he said that anytime you have hydrogen ions in solution, it's an acid. And similarly, anytime you have hydroxide ions in solution, so the NaOH, the sodium hydroxide, is going to dissolve in solution. We're going to get sodium ions. We're going to get hydroxide ions. And if you have a collection of hydroxide ions in solution, that's a base. So that's the Arrhenius concept, a real simple. The only problem is that there's loads of other things that cause water to become acidic or basic by either taking one of the hydrogens and therefore leaving a hydroxide ion, or donating a hydrogen ion and therefore causing it to be acidic. And so we have the idea of strong acids and bases, and you should understand that strong acid and base is a strong electrolyte, which means it has complete dissociation. So the idea of complete dissociation, and these are both strong, so we have a strong acid here and a strong base here, and complete dissociation means if I put in 0.010 molar of this, it will give me 0.010 molar hydrogen ions. So strong means complete dissociation. Every single one of these hydrogens will come off and remain as an ion in solution, and none of them will stay here. So that's the idea of strong acids or strong bases. Now there's only 8 strong bases and 7 strong acids, and really at this level you're going to have to memorize those. If we're going to do some calculations, just to remind you of what pH is. pH is the potential for hydrogen, and really it's just a way of giving us a whole number to express a hydrogen ion concentration. So if we have a very high hydrogen ion concentration, our pH gives us a very low number. And if we have a very high hydroxide ion concentration, our pH is a very high number. And so you solve for pH by taking the negative log of the hydrogen ion concentration. So let's do that right here. So if I was going to solve for the pH here, it would equal the negative log of 0.010. And that equals 2. Okay, so the pH of this particular situation is going to be 2. And I know it's going to be 2 because I put this in, completely dissociates into this. So doing calculations, pH calculations with strong acids and bases, very easy, not a big deal. Let's look at the strong acids and bases real quick. You'll see the 7 strong acids right here, HCl, HBr, so hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, HClO3, perchloric acid, HClO4, nitric acid, HNO3, and sulfuric acid, HSO4. So these are all strong, and this is it. And so you got to memorize these. You got to know these. Very important to be able to recognize these when they come up, because that complete dissociation will be important to know when you're doing calculations. Strong bases as well. These ones all completely dissociate. A little bit easier to memorize the strong bases because look, these are all your group 1s. There's your lithium, sodium, potassium, rubidium, and cesium. And then these are your group 2s. If you just exclude the first 2 and go down the list, you have calcium, strontium, and barium. Now, one thing I want to point out is notice that, of course, for calcium, you're going to need 2 hydroxides, and for strontium, you're going to need 2. And then also over here, for sulfuric acid, you need 2 hydrogens to go. So the assumption might be that if these are strong and they completely dissociate, well, each one of these H2SO4 molecules is going to yield 2 hydrogen ions plus a sulfate ion. Well, that's not the way it works, actually. As far as strong goes, it can yield 2, but it doesn't. It typically just yields 1 for sure. So when we're talking about strong, we're actually, in the case of this is an acid, we call this diprotic. And diprotic means that it has 2 hydrogen, right? It actually only will release 1 for sure. And this will stay like this. And so when we're talking about the strong acid, these actually end up all being equivalent because this one really does dissociate 1 for sure in the sense of being strong. And that also works for the dibasics. So calcium hydroxide is not going to get off 2 hydroxide ions. It'll just give off 1. But it will give off 1 completely. All right. So that also leads us to understand that the ions that go with these strong acids are what we call neutral. So these are neutral ions. Now, neutral ions are important for us to understand because they show up and they help us to solve other things and figure out what's causing things to happen. Because since they're neutral, they just don't interfere, and they hang out by themselves, and they don't cause any trouble. So, for example, with the bases, it's real easy. You got all your group 1s here; they're all neutral. And what we're saying is that when lithium is in water, right? When lithium is in water, guess what? It remains as lithium in water. So now let's look at another cation. So this particular cation is neutral, meaning that it's not going to do anything to the water. But the cation ammonium, for example, NH4, if I put that in water, you see what's going to happen here is the ammonium is going to turn into ammonia. It's going to donate, actually, a hydrogen to the water, making it acidic. And so this ends up being an acid. Or actually, we could write it. I just taught you about the Arrhenius model, so I will do it like this so that you can sort of visualize it in the sense of the Arrhenius model. But actually, when we talk about the Bronsted-Lowry, we're going to learn that this hydrogen actually ends up attached to the water molecule here. And so that also goes for these anions. So in the case of these anions, when chlorine is in water, guess what? That's it. It doesn't do anything. It ends up just staying in water. But you'll notice that this cation right here, what did it do? This cation made this solution acidic, right? So the cations that are not a part of the strong acids will cause the cations that are not a part of the strong bases will cause solutions to become acidic. And the anions that are not a part of the strong acids will cause solutions to become basic. For example, let's do an example with that. The phosphate ion, for example. Phosphate ion is not part of any of our strong acids up here, right? So when the phosphate ion goes in water, plus, oopsie, I don't know what that was, plus water, what happens is that it takes one of the hydrogens from the water, and we get HPO4 plus OH. And notice there you are with your hydroxides in there, so this has become basic. Okay, so so all that to say, these are strong. They completely dissociate, and the anions and cations that go with them are totally neutral, meaning that they will never interact with water to create any more acid or base, any more acidity or basic solution, or any more increase in hydrogen ions or hydroxide ions. And so then, you know, if we were to look at a couple more examples, why would an aqueous solution of any of these things, let's just say, for example, NaCl, why can you assume that that is going to be completely neutral? If I dissolve that in water with a pH of 7, well, what's the pH going to be? Well, look at it. Sodium is a neutral ion, right? And if you don't remember back here, look at that. Sodium is a neutral ion, and chlorine is also a neutral anion. So it's going to go like this, and the pH, you can be sure, is going to be 7 still, because it's not going to cause any interruption in the water. Similarly, some other ones. What about potassium nitrate? Potassium nitrate is going to cause everything to be completely neutral, because that is a neutral cation, right? It goes with a strong base, and that's a neutral anion, goes with a strong acid. Other ones, for example, lithium perchlorate. Lithium perchlorate, that's going to create perfectly neutral environment when it dissolves. Barium bromide as well. All these are going to create neutral solutions when they're dissolved in water. They will not change the acidity at all, or alkaline. And let's see, I already got that one, so I think there's one more for sure. Cesium iodide also. So all of these, look, what do we have all these in common? All these are combinations of neutral anions and cations. So you'll have completely neutral solutions when these salts are dissolved in water. All right, so that's the introduction. Next time we're on to understanding the Bronsted-Lowry acids and bases, and we'll talk about weak acids and bases and do some calculations.